Hello everyone, I hope you are doing well. In today's lecture, we are dealing with the computations in critical flow. This is second part of chapter 10, which is entirely about calculations in critical flow. Before we start the discussion, we should first recapitulate a little of last week's lecture. As you see here, we talked about fluid number. In open channel flow, the driving force is the component of gravity along the channel bottom. Therefore, it is clear that the effect of gravity is very important in open channel flow. We define third number as the ratio of inertia force to the gravity force. And we said that it should be equal to velocity over square root of gd. Here d is hydraulic depth or hydraulic mean depth, which can be calculated using A over T. A is the cross-sectional area and T is top width of the channel or top width of cross-section. Uh, Considering the value of third number, we divided flow regime in three different conditions. You see here, when the third number is greater than 1, we call this is supercritical flow. And when the third equals to 1, we stated that flow has the critical flow condition. And for the third values less than 1, flow is called subcritical flow. Here you see uh, channel bed and location of supercritical and subcritical flow. This is Y0 belongs to the or normal depth belongs to the supercritical flow condition. And you see in supercritical flow condition, the depth is below the critical depth. Therefore, it is expected that flow velocity would be higher than the uh, normal condition. For the case of supercritical flow, subcritical flow condition, you see this surface belongs to the subcritical flow condition. The normal depth, this is our normal depth, is greater than critical depth. Therefore, the cross-sectional area is higher than normal condition, and it creates less velocity. Therefore, we said that this is supercritical flow. Here, I have a question also in order to clarify why we study these different flow regime, different flow depths, and why we classify flow in the super or sub or critical flow condition. Here I summarize the reasons. Let's review together. We can engineer a canal that handle supercritical as well as subcritical flow without any problem. The problem arises when we have a channel that for whatever reason transition happens from supercritical to subcritical flow. This transition is a type of rapidly varied flow and is known as a hydraulic jump. Let's show here hydraulic jump here. The first reason said that when we have supercritical flow, and it is possible that we see a transition from super to subcritical, and this is the reality of flow. Actually, in open channels, flow always would like to have a subcritical condition, and when we have a supercritical like this, it is possible that we have a transition like here. You see that I have a transition. Draw the transition from super to subcritical. But this is a very fast here. It is a very fast transition. and this is a unstable condition, which is called hydraulic jump. I will talk about this issue later in different next sections, but let's come to the uh, answer and continue the second reason. Therefore, when we design channels, we pick the channel shape and the bed slope. Yes, we already talked about this issue. For the design of canals, we select first channel shape and bed slope. Therefore, we should select these two parameters so that they are solidly supercritical or subcritical, but nothing between. As I explained, because when it is between, the flow is not stable. Therefore, we must also calculate the critical slope of our channel to ensure that the slope we have chosen does not come too close to the critical slope of the open channel. In brief, the aim is to have a flow regime in the channel same to what we expected when we sized or we designed it. Okay, here I provided a very short video from RWTH University that shows critical flow, hydraulic jump, and subcritical flow condition. Let's see to watch together. Here you see a subcritical flow. This is a supercritical flow, and we had a hydraulic jump. Let's review again. This is subcritical, again supercritical. Hydraulic jump appeared here. This is the location of hydraulic jump in Kirby's minutes, supercritical. And again here you see I have a supercritical flow, and this is hydraulic jump. Okay, now let's continue with the three different kind of problems that we might face when we are dealing with the calculations of critical flow. In the first case, we see that critical depth is given, and you need to calculate or to determine critical velocity. In the first case, when we have a critical depth, it means that we have the geometry of the canal. Therefore, you can easily calculate velocity with respect to the definition of the celerity. You remember this term is the celerity, or in other words, when the depth equals to depth of the flow equals to critical depth, the velocity is equals to the celerity, and you can easily find it by the square root of g times dm. We already said this is hydraulic mean depth. And when you have the critical velocity, the corresponding discharge would be the A times critical velocity. Within this A, you know that we use again critical depth to calculate the flow surface area. The second type of questions is when discharge is given and you are expected to find critical depth. As you see here, we need to use trial and error method to find critical depth, and to this end, again, and we can use this equation in which we should solve this equation for YC iterative via iterative method. And the last type of question is that we are expected to calculate critical slope when we have the morning roughness. Actually, this is the common type of the problems that we are faced in the practice. And to find critical slope, we solve Manning. This is Manning. We solve Manning equation for critical slope, in which for the term R, hydraulic radius, we will use the already given critical depth. Here we have some examples that will show how we can solve different kind of problems based on different classes that we saw in the previous slide. Example 1 says determine critical flow velocity and critical discharge for the given rectangular channel. This is my rectangular cross-section. Flow depth equals to critical depth, and it is given as 1 meter. Bottom width is 4 meter. And when I know that the depth is YC, the depth is critical, therefore the corresponding velocity is the celerity, and I can directly and simply use this equation to find the velocity equals to g times square root of g times d. mg is 9.81 and dm equals to a over t. A is b times yc equals to 4 times 1 and divided by a over t divided by t. T is the top surface and it is equal to b in a rectangular cross section, which is 4. Therefore, velocity or critical velocity is 3.13 meter per second, and we can calculate discharge through the multiplication of the velocity by the cross-sectional area. Again, here cross-sectional area equals to 4 times 1. Let's see another example. For a trapezoidal channel with a base width b equals to 6 meter, side slope x equals to 2, which means for each one vertical makes 2 horizontal, and Manning's n equals to 0.02. Calculate the critical depth, critical velocity, and critical slope if it is discharge. Its discharge equals to 17 cubic meters per second. This question is the combination of the second and third type of the question, and let's see how we can determine first critical depth, then critical velocity and critical slope. This is the trapezoidal channel, therefore the area equals to b plus xyc times yc. We know this formula, and what I did, I only replaced the y with critical depth because the question said me we consider that the flow in with this discharge with this parameters given is in critical condition. Therefore, I use yc everywhere that I have y. Therefore, I can find IA equals 6 plus 2yc times yc, and b here, b is the top width equals the bottom width plus 2xy, and here again, b or top width will be 6 plus 4yc. What I need to calculate hydraulic mean depth equals to a over b, and from here with the legal algebra you can say that dm equals to 3 plus yc times yc over 3 plus 2yc. This is hydraulic mean depth. Therefore, I can use celerity formulation to find discharge. What is given here? Discharge equals to A times Vc. Then the depth is critical. The associated area is also can be denoted by A sub c, and corresponding Q can be calculated. Q is already given, and using this equality, we can find unknown YC. I put 17 here, and I know AC. This is my critical depth. This is my critical area, and I put critical area, and I need to take the square root of d g times dm. This is the square root of g times dm. And here we need to do some simplification and a little algebra to reach this expression. And from here, you can solve this relationship for YC, and you will see that YC equals 0.84 meter. Now YC is at hand. You can come back to the uh, first line and calculate area. Cross-sectional area is at hand. Therefore, velocity can be calculated by uh, dividing discharge over cross-sectional area, and therefore you can see that velocity is 2.6 meter per second. Now I know the velocity, I know the critical depth, and I can solve Manning roughness for critical slope. And in Manning roughness, you know that we need to find hydraulic radius. And for hydraulic radius, we need to first determine the wetted perimeter. And this is the general formulation for wetted perimeter in trapezoidal cross sections with a critical depth. And x is side slope equals to 2 given here. Therefore, my wetted parameter in critical flow condition would be equal to 9.76 meter. Hydraulic radius can be obtained via the already obtained cross-sectional area and wetted parameter. You remember A was the 6.45. Therefore, 6.45 over 9.76 will produce 0.66 meter hydraulic radius. Therefore, you can use Manning equation to find critical depths. We already calculated. N is given. Manning roughness equals to 0.02. And now you know the hydraulic depths, and you can easily calculate this fraction, and the answer should be powered by 2, and the results shows the critical slope equals to 0.005. Here I have another example. Determine critical depths for depths of rectangular channels for the given discharge and bottom width. You see here I have the same question, but with the first example, but YC is not at hand, is unknown, and I only have B. Determine critical depths of rectangular channel for the given discharge. Sorry, discharge is also at hand, and now I have a question from the second type. Discharge is at hand, and channel geometry is at hand because I know B, but I would like to determine critical depths. If you were given a flow rate and the shape of a channel like the rectangle, like this example, we have a top width of B, which is equal to the bottom width. Yes, top width in rectangular channels, T will be equal to B. Therefore, it will help us to find the method that instead of trial and error method, we can calculate the YC directly. From the third number, when we have a critical flow, we know that third number is equal to 1. Therefore, celerity equals to a square root of GD. Yes, this is celerity. And we know that Q equals to, therefore, in critical flow condition, Q equals A times square root of G D. This is a general formula, but for the case of rectangular cross sections, like here, we can replace A with B times B YC, B times YC. And therefore, we can say that YC, and I have a YC to the power of 1/2 here. Well, therefore, I have YC to the power of 3/2 equals to Q from here, Q over B square root of G. Here I have a Q over B, yes, Q over B. We define a new parameter which is called unit discharge as a lowercase q equals to Q over B. This is unit discharge, and therefore we can say that YC to the power of 3/2 equals to Q over or lowercase q over square root of G. Let me explain what is unit discharge. Actually, when in rectangular cross section, you can divide Q by the bottom or top width, which means that you find how much water uh, passes from the different segments of the cross section, each of which has 1 meter. Yes, each has 1 meter. For example, if here B is, for example, 4 meters, and when you divide Q by 4, it means that you separated this entire Q for 4 equal segments, each of which pass from one of those 4 segments. And definitely summation of those unit discharge will give you the entire discharge. This definition only defined here to make some simplification to calculate critical depths. And when you know the B top feed in a rectangular cross section, you can easily use this formula, which comes from here. This is a transformation of YC. I solved this for YC, but I replaced Q over B or capital Q over B with the lowercase q, and you can directly solve this problem and find YC. For example, if I know that if I give some, yes, this is an example I have here. I'm looking for the critical depths when B is 3 meter and flow rate or discharge is 5.3 meters cube per second. Money roughness also given, therefore I can calculate the other parameters like normal depths or slope of the critical slope of the channel. From the Manning equation, this is the solution for the case that the flow, yes, for the case that the flow is not in critical condition, yes, I assume this is a normal for a normal or for a uniform flow condition. I calculate A equals to by. This is y normal depths, and I calculate weighted perimeter with normal depths. You see that like what we studied in chapter 2, I can find normal depths of uniform flow using the Manning equation. And from a trial and error method, yn would be zero point 0.4. Yes. However, I would like also know that what is the critical depth for this channel shape. I have a channel shape, and I have the rectangular channel. Therefore, I can calculate unit discharge. As you see here, unit discharge is Q over B, which will be 1.767 cubic meter per second, again per meter. This is at hand. YC equals to cube root of the Q square over G, which equals to cube root of 1.76 the power of 2 over 9.81, and therefore critical depth for this channel is 0.683. And let me ask a question here. Now, you see that for this rectangular section, critical depth is 0.6 and normal depth is 0.4. And what is the flow condition for this? You see, normal flow is below the critical depth, and it means that we have supercritical flow condition in this channel. Okay, this is all for today. I think we can jump to the next chapter in the next lecture. Have a good day.